Okay, so we've wrapped up we've wrapped up the textbook's part 2. So the textbook is actually split into 3 parts, even though we only do the course in 2 semesters. We finished up the AC portion, and now we're going to move into the frequency domain portion. The reason the class is actually called Frequency Domain Circuit Analysis, it's because of this chapter, right? So the topics we're going to start talking about now are a little bit more mathematical in nature. We're going to start allowing the omega, our frequency, to change, or be a variable, right? Which starts to move us from the pure AC concepts of phasors, which are mostly applicable to things like power, where you have one frequency. And this moves those concepts to a place where with variable frequency, we can start to apply them to communications, to music. If we want to record music with a microphone and play it back on our MP3 player, right? You've got to be able to accommodate more than one frequency. And so we're going to see how that happens. But we're going to use the stuff we've already been doing. We're going to just expand our definition. So I'll give a little more motivation, but then we're going to talk about something called the transfer function, which is a concept you're going to see come back up all the time. This becomes really the language and the tool of electrical engineering. Everything is talked about in terms of its transfer function. So this is a really important concept for you to take forward into future classes. Next semester, so all of these concepts now, especially the concepts we're going to talk about in these next couple of chapters, you will absolutely see them next fall in systems and signals in your EE221 class. So you really want to start to see this concept and get a good grip on it, because we're going to do it a little bit of a more simple case now, but then in the fall you're just going to dive in, and it is just going to be the way you do problems and the way you address almost everything else from this point out, right? So I definitely want you guys to really understand these concepts so that as you learn the deeper math in the next semesters, you'll be more comfortable with it. We'll talk about how these now lead to ideas of resonance and filters. We haven't really talked about filters yet because we've always dealt with one frequency, right? So, but now we need to be able to deal with all the different ones. Okay. So, again, we've already seen that things like impedance, right, have an omega in them as a variable. But we've always defined it as a single value. We've said, oh, frequency coming out of a wall socket, that's 60 hertz, right? So we find the angular frequency, we write that down, right, 2 pi f. And that's our frequency for the entire problem. And we just plug that in everywhere we see an omega. And then we've solved it algebraically or with whatever other techniques we want to use. But now we're going to allow that omega to change. So frequency response is talking about the circuit's behavior as the signal frequency. So the signal is the voltage or the current that's moving through our device, right? And it can also be considered as a gain and a phase with frequency. So when we've talked about phasors, we always wrote it down, right, as a magnitude and a phase of whatever voltage or current we're looking at, right? So we would write this down as literally just like 3 with a 45-degree phase angle. And we know that that's 3 volts if it's a voltage, right? 3 volts at 45 degrees, but we've assumed omega. Well, essentially what this is telling us is that there is a gain, which is like the magnitude, and a phase at every different frequency, right? If we plug different numbers in for omega, we would get something different out here. So now when a voltage goes through, we're going to see that, in fact, I can take an input voltage or signal. I could multiply it by, if I had an impedance and it was in phasor form, I could multiply it by that impedance. And at each one of those frequencies, if I were to walk through and plug the number in, I would see a different number come out of the multiplication because the omega changes. And that change is what we call gain. Now we've used the term gain before. Where do we see gain? Where did we talk about gain in the past? Op amps, that's right. So we've used that idea, and with an op amp we've said, oh, when a voltage goes in, it gets multiplied by whatever, depending on the op amp, right? If I have a simple inverting op amp configuration, like this, right? We've said, oh, this is the feedback resistor, this is the input resistor. So if I have V in and V out is just V in times, in this case, the gain, negative RF over Rin, right? So we've seen this concept before. In this case, we weren't necessarily dealing with frequency because this is just a DC voltage, but we saw this again with AC, right? We did these, but we defined a fixed omega. So the omega term never really ended up in the final form. We didn't really see it. But if we left it in there as a variable, guess what? This gain would be frequency dependent. It would be a gain of omega, right? A function of omega. And so we're going to formalize now how we treat this idea of gain at different frequencies for all of our circuits. So this is the idea of the transfer function. The transfer function is this frequency-dependent ratio. We did this a few times as well with op amps, right? We said, well, what if I don't really know what Vn is yet? Well, we found the gain by just dividing by Vn, right? And we called that the gain. Book used the symbol A for it several times. Right? So the gain of the op amp was the output voltage divided by the input voltage, right? And that was this RF over Rin type of a term, or if it's a different configuration, we found out ways of figuring out what that value is. So now imagine that that has the omega in it still. This gain is now a function of omega. This is our transfer function. So the transfer function is defined as the ratio of the output to the input. So if we were to look at this as a simple block diagram, inside this box there's a bunch of circuitry. We don't really know right now what it is, but it could be op amps with capacitors, inductors, whatever, anything, right? But a voltage goes in, or a signal, could be a voltage or a current, goes in, and a signal, a voltage or current, comes out. Whatever that output is, if I divide it by my input, I calculate the transfer function. And of course, if there's an omega in here, there's probably an imaginary part as well, right? And that imaginary part would become a phase shift. Right? So we end up with a magnitude portion of the transfer function and a phase portion of the transfer function. Okay? And so h of omega is oftentimes split into those two halves. And we see it written as its magnitude and its phase. Just like phasor form, except that it's still dependent on omega. Both the magnitude and the phase are dependent on omega. So as we put different frequencies in, this will do something different to it. But ultimately, if we look at this as algebra, what's going on? Well, what do I do if I want to get the output? If this is my and I know h, if I know the transfer function, and I say, I'm going to put in, I don't know, a 15 volt signal at 60 hertz. How do I know what comes out the other end? Yeah, it's just algebra now. So the transfer function allows us to treat our circuit, that whole mess of circuitry that we've condensed into this box, as now just an algebraic equation. Whatever that is, I can multiply it by the input, and I will get the output, because that's the definition. So it makes it really easy. Once I've found the transfer function of a circuit, I can find it without needing to know the input. And again, up till now, most of the time, we've been given this value of this supply, right? Now we don't need to worry about it. It's just an unknown. It's just a Vn, like it was in some of these op amp problems. So that allows me to analyze my whole circuit and its response, figure out what the circuit's going to do, regardless of what I put into the circuit. That's probably a good idea, because if I want to build an amplifier, right, my phone, which I need to silence anyways, right? But my phone, when I want to play music and I plug in some headphones, right, I get an amplified signal that I can actually hear with my ears, right? It gets louder. When I adjust the volume, it gets louder, softer, whatever. Well, I want that to work regardless of the song that I decide to play, right? I mean, I guess if you have a particular kind of music you don't really like very much, you might not care if the phone didn't amplify that, right? But I want to get the best reproduction I can. I want to get all the low frequency stuff. I want to get all the high frequency stuff, at least in the range that I can hear, right? And I don't want to know ahead of time when I'm designing a phone what song someone's going to play. That would be kind of pointless. So the transfer function is the thing that you're working on. When you're the electrical engineer, you say, well, my circuit will work like this for this whole range of frequencies. You can't make it work for all frequencies, but you can pick, and you can design to work over the range you're interested in. So if I'm building an audio amplifier for a phone, I can say, well, humans can hear from 20 hertz to 20,000 hertz. So as long as I can reproduce and make happen what I want to happen over that range, great. Whatever they put in, I know the output will just be a multiple based on what I've designed, right? And that multiple is a gain, it gets louder, right? In fact, some of the students in a couple of the juniors this year in the microelectronics class that I'm teaching, they actually designed headphone amplifiers for their phone. That was their project that they chose. So if any of you know Will McDonald and Vin Moretti, right? They actually made an Altoid box amplifier for their phones, right? So they made 2-channel amplifiers, one for the left and the right. They plugged their headphone jack from their phone into the box, and then they plug their headphones into their Altoids box, and it boosts their headphones, and they can power their headphones, probably enough to blow their headphones up actually. But they have those really high-end, expensive headphones that are really nice, and they want to be able to make them loud enough that they can basically be desktop speakers. And so they're driving them, so they have a battery in that Altoids box that adds extra power, right? And so they were very concerned. They designed a circuit that made sure that it had really good response across the range of audio amplification. They didn't worry about what was going in or what was coming out. They just designed the transfer function of the circuit. So it's a very applicable idea, although very mathematical. So there are 4 flavors, if you will, because the input and the output can be voltages or currents. So we have the 4 mixtures, right? If we have an input voltage and an output voltage, we just say it's a voltage gain transfer function. If we have current in and current out, this one down here, current in and current out, it's a current gain, right? Current goes in, gets multiplied, gets a current out. Easy, right? The other 2 that you will hear about, and you should be familiar with the terminology so that you understand what they're talking about, is relating it back to the idea of Ohm's law. So you'll see transfer impedances listed, and that just says that the transfer function looks like a resistor or an impedance, because a current goes in and a voltage comes out, right? So if I look at my output VO, and it looks like H of omega times I in, right? V equals Z times I. So the H right here looks like an impedance Z. And so we call that a transfer impedance. The opposite case of a voltage in and a current out, we call a transfer admittance. Just move this to the other side, change the subscripts. Right. So then this moves over here, and it becomes an admittance instead. Right? Like a conductance. So those are just ways of discussing the general form. And so you'll oftentimes hear about, you may say, well, I need a transimpedance amplifier. You might say, well, what, a transimpedance amplifier? What the heck is that? Transimpedance is a transfer impedance amplifier. It just means it may be an op amp, and you're setting up your op amp such that current goes in and voltage comes out. That's it, right? That's what it means. So it's just a little terminology, good to tuck it away for future reference. So let's find the transfer function, see what it actually looks like. We're going to leave omega as a variable. So this is a basic RC circuit. I don't know why some days this thing erases really well and other days it does not. I may as well not have an eraser. So in this case, we have our basic RC circuit. We know what the RC circuits look like. We've solved those in the time domain. We've solved them in the phasor domain. Right? We know it's just going to give us sort of an exponential output. Right? In this case, it's going to charge up to an exponential if this were DC. But if I don't know what that input is, how do I deal with it? Well, let me find the transfer function. So I'm going to put it in phasor form. Right? And that's what's happened on the right-hand side. Going to phasor form, R stays as R, and the capacitor just becomes 1 over j omega c. But I don't know omega. So in our previous chapters, we've always plugged in omega and found the number, right? So you would have negative J5 or something like that for a capacitor. Now you have to leave the omega in as an unknown. And now solve. Solve for the output as a function of the input. So I can apply KVL, KCL, whatever tools that I want. So if this is a simple loop, let me just do KVL. Right, so KVL around the loop. And we're going to I'm going to start in this lower left-hand corner. I get negative Vs plus Ri, right, if I have a current in the loop, equals I times j omega, plus, equals I times 1 over j omega c equals 0. Right? And I can now solve this for I. And then when I'm done, though, I want to get V out. So that's what it's asking me for. I want the transfer function V out over Vs, a voltage gain transfer function. So the output voltage has to come from this current that I found, right? And so I can write that down. And I know the output voltage is just going to be I times that 1 over j omega c, right? Once I find I. So I can solve this. Vs is like a constant, basically, right? It's a variable. We don't know what it is yet, but it's not the variable we're trying to solve for. So we can treat it as if it's a constant, just as if we had defined it with a value. All right, so I can move it to the right-hand side. Let me collect my terms. So I'm going to have I times R plus 1 over j omega c equals Vs. And so now I can find I by dividing this over. Can you guys see that marker okay? Is that going to be any better?
The blue is better.
The blue is better? The black is, oh my, oh. Some days my remote is, I just can't trust it anymore. This black is not very good either. Now, blue, right? This happens. We're nearing the end of the semester and all of the markers are running out. I don't believe that. Okay. So I have I, but I really want V out, right? So I need to take I times this j omega c. So VO equals Vs, right, times Vs over R plus 1 over j omega c times 1 over j omega c. I now have the output voltage in terms of my input voltage times something. So if I divide by Vs, I now have H of omega. So my transfer function, which is the output voltage over the input voltage, is this 1 over j omega c divided by r plus 1 over j omega c. Now, I can clean that up, right? I can do the algebra to get that into a little bit nicer form, which I really ought to do, especially because we don't like j's in the denominator, right? They are ugly. No one really likes that. So in this case, if I were to clean it up, I would multiply top and bottom by j omega c. So the j omega c here, right, if I went to j omega c and j omega c, right, on the top and the bottom, that would cancel this one. I'd be left with a 1. And on the bottom here, it's going to distribute in. It's going to give me a 1 here, and it's going to give me a j omega rc. So 1 plus j omega rc. And that's a much nicer looking version of the transfer function, right? And there we go. So now, if you hand me this RC circuit, and in fact, that's pretty generic, right? So now for any RC circuit, we know what the transfer